Butterworth filter. A Butterworth filter is a type of active filter, where the frequency response of the across its passband is relatively flat. Because of this frequent response, Butterworth filters are also known as maximally flat filters or flat filters. Using Butterworth filter technique, you can design all types of filters, i.e. high pass, low pass, band pass, etc. In this tutorial we will concentrate on low pass filter design using Butterworth filter technique. For more information on typical low pass filters, whether active or passive, read these tutorials: passive low pass RC filters and active low pass filters. Introduction. There are mainly three considerations in designing a filter circuit. They are: the response of the passband must be maximum flatness. There must be a slow transition from passband to the stop band. The ability of the filter to pass signals without any distortions within the passband. These distortions are generally caused by the phase shifts of the waveforms. In addition to these three, the rising and falling time parameters also play an important role. By taking these considerations, for each consideration one type of filter is designed. For maximum flat response, the Butterworth filter is designed. For slow transition from passband to stop band, the Chebyshev filter is designed, and for maximum flat time delay, Bessel filter is designed. Butterworth filter. At the expense of steepness in transition medium from passband to stop band, this Butterworth filter will provide a flat response in the output signal. So, it is also referred as a maximally flat magnitude filter. The rate of fall-off response of the filter is determined by the number of poles taken in the circuit. The pole number will depend on the number of the reactive elements in the circuit, that is, the number of inductors or capacitors used in the circuits. The amplitude response of nth order Butterworth filter is given as follows: Vout/Ven equals 1/(1 plus f/fc 2n, where n is the number of poles in the circuit. As the value of the n increases, the flatness of the filter response also increases. F equals operating frequency of the circuit and Fc equals center frequency or cut-off frequency of the circuit. These filters have predetermined considerations whose applications are mainly at active RC circuits at higher frequencies. Even though it does not provide the sharp cut-off response, it is often considered as the all-round filter which is used in many applications. Butterworth approximations. As we know that to meet the considerations of the filter responses and to have approximations near to ideal filter, we need to have higher order filters. This will increase the complexity. We know the output frequency response and phase response of low pass and high pass circuits also. The ideal filter characteristics are maximum flatness, maximum pass band gain and maximum stop band attenuation. To design a filter, proper transfer function is required. In order to satisfy these transfer function, mathematical derivations are made in analog filter design with many approximation functions. In such designs, Butterworth filter is one of the filter types. Low-pass Butterworth design considerations are mainly used for many functions. Later we will discuss about the normalized low-pass Butterworth filter polynomials.